The Medical AI Podcast.
Hello, and welcome to the Medical AI Podcast, a 30-minute thrill ride of big ideas. We are Dr. Felix Beecher and Joe McKeating, and we talk to a range of top guests, from scientists to industry innovators to philosophers.
Welcome to the Medical AI Podcast. I'm your host, Joe McKeating. Today I'm joined by Davit Buniatyan, the CEO of Activeloop. Activeloop automatically connects unstructured data like audio, video, image, and point cloud data to machine learning models. It is trusted by the likes of Google, Intel, Waymo, and Bayer. Davit, thanks for joining me today.
Thanks a lot, Joe. Thanks for the invite. Super excited to be here.
So you were 20 years old doing your PhD at Princeton, which, as an aside, before our conversation, I went and looked. The average age of a doctoral student in the United States is between 31 and 32 years old. So pretty incredible there that you're 20 years old at Princeton doing your PhD. You were studying the neural pathways of mice, and inspiration came to you that based on that research, we need to rethink the data infrastructure for machine learning and artificial intelligence. I think that'd be a really fun place to start this conversation. Can you kind of go back to that time in your mind and tell us that story?
Sure. First of all, it's good news that it's not too late. It's still early to go back and finish my PhD. This has been one of my regretful decisions, either doing the company or finishing my PhD, and I decided that likely I can have bigger impact in computer science by doing what we are building now. And I'll get into details what we are building now, but back then in 2016, I got accepted to Princeton. I was initially in a computer vision lab, but then later, apparently my professor, who was supposed to be my professor in computer science department, decided to leave to Silicon Valley to start his own self-driving car company. So I had to switch labs, and I accidentally or incidentally found advisor Sebastian Son, who is one of the leading scientists in connectomics, which is a new branch in neuroscience, trying to reconstruct the connectivity of neurons inside the brain to understand how the brain works. And I was super excited to apply deep learning applications in the neuroscience domain. And the problem and the challenge was pretty massive. We started with dealing with tens of hundreds of terabytes of data, and then later it scaled to petabyte scale data sets. And we had to essentially rethink all the infrastructure tooling from the beginning. Apparently in machine learning, and not only in machine learning, but also in systems, when you scale the problem by 10 times, the problems that were edge cases, let's say that there was an error on every 1 percentile, now they become like 10 times bigger. So you have to make the deep learning models more accurate. The system infrastructure should be more reliable, way more reliable, to be able to handle all those edge cases. And we had to rethink a lot of tools. The problem that we had is processing petabyte scale data set on the cloud was costing us a single inference was costing us $1 million. And our job was to reduce the computation cost by 5 times by rethinking how the data should be stored, how it should be streamed from the storage to the computing machines. Should we use CPUs or GPUs, and what kind of models to use? And those insights and the problems that we were facing helped to shape the company, and that's how we applied to Y Combinator and moved to Silicon Valley.
So I think for a lot of listeners, interesting that you said there, improving the efficiency by 5 times would still be $200,000 in inference, which is seems pretty expensive to an outside listener, right?
Yeah, totally. The problem is that we also might mess up a couple times. So we needed to have kind of enough failure point. Like sometimes he could run a pipeline that will run on hundreds of GPUs on the cloud, and the output is like everything is black. And the reason why is everything is black, there was very one minor mistake. Let's say when the neural network was doing the processing, the data was not normalized before shipping to the neural network. So we had to have enough capacity to be able to do the mistakes. Even if the single run is, let's say, $200,000, then we know that we have a couple shots. And actually, that project itself has been a big project under, I think, if I'm not wrong, it was under Brain Initiative. And the Micron project was like, the total budget was 100 millions across multiple universities, and there were multiple groups working on it. And then each group had its own responsibility. And our lab was responsible for, once the data has been imaged, which means that the mouse, basically a small part of the mouse brain has been cut, and then using electron microscope image, then we receive these images, then we can do the computer vision processing, and as an output get all the connections of neurons connected to each other. And one of the biggest challenges was like, even if you, let's say, do a single mistake confusing, hey, this neuron connects to the other neuron, where like for a AI model, it could be just, okay, there's a classification problem or a segmentation problem, just one digit wrong. It actually has a cascading effect on the whole total graph connection, because now a single miswire can cause the whole connectivity of your connections wrong. And then later neuroscientists, when they do their research to understand, for example, how the learning is happening inside the brain, they can be totally confused. So I think aside from having the cost issue, there's also, you have to be very, very careful with the specific, with what we call like butterfly effect errors, that a small problem in the early part of the pipeline can just like have a cascading effect on the output of the end result. And you have to be very, very careful in crafting this whole system.
And it sounds like at that time, from what you just said, you're mostly dealing with image data, right? When you're taking these slide images, you have to figure out how to build and fine tune these models with that at a much more cost efficient way. But now at Activeloop now, and we'd like to hear the story about how this transitioned to Activeloop, the company, but at Activeloop now, you're not just dealing with images and computer vision, you're also dealing with audio, video, a lot of what would be oftentimes considered unstructured data. Is that correct?
Yes, totally. So what we found out is that the tooling and everything that we developed was focused on not just images, but biomedical volumetric images, which are 4-dimensional images, think of them. And then the challenge when they're not suitable, like you couldn't fit the text inside or audio, but all the methodology and all the insights that we built out there, where actually you could expand, like you can, instead of fixing this 4-dimension, you can go to 3-dimension, go just like usual images, go to 2-dimension, or audio waves, or 1-dimension, text as well, and essentially make it a very generic solution. And that's how Activeloop's Deep Lake has been born. We put the format, how to capture this multi-modal, multi-dimensional data, open source about 4 or 5 years ago. Since then, it has been number 2 trending across all GitHub repositories, number 1 Python languages. We almost reach out about 2,000 data science and data engineers in our community. And the main insight was there, like the reason why this system worked very efficiently is because of the AI native format. These deep learning models, they don't really care if it's an image, it's an audio, or it's a text file. You have to convert them into this n-dimensional arrays, or what people call tensors, and feed these tensors to the models. And one of the key, like I'll say mind shifts is like, why don't we actually store the data in tensors? While the user is not worried about if it's a tensor, they can just drop in their images, we will automatically structure them into this n-dimensional arrays. And then once the model needs to access it to either do the training process or run the inference, then we can very efficiently stream the data from the storage to the compute to do the processing itself without doing too much data transformations.
And so should we think about tensors as a data format? Is that what listeners should be getting from that, or is that the wrong way to think about it?
Well, technically, tensor is a mathematical construct that like a lot of computer scientists took over and started naming things inside these frameworks that are doing deep learning processing, such as TensorFlow or PyTorch. And there's also another one called JAX. I'm not getting into too much technical details, but I think the easiest manner to think of those is that, hey, you have a table or like an Excel spreadsheet, and like traditionally all databases, they have been like each column is just a one-dimensional data. Could be just numbers, could be maybe small the strings or words, etc. But when you try to put, let's say, an image inside a database or inside an Excel spreadsheet, it didn't work out. And what these tensors now enable you to do is like taking this column and now saying, hey, instead of being this one-dimensional array, now we can make it two-dimensional, three-dimensional, or n-dimensional data. So now I not only can just easily put images into my tables, but I can also put like DICOM files, which are the MRI scans or CT scans or X-ray images, into the tables along with the, let's say, patient data, to be able then train a model to do, for example, cancer detection inside those images. So that's the main kind of the mind chip. And if you ask, okay, why do we need to do this? Because the way currently a data scientist in any organization, they work with the data, it's very similar to how we use our desktops. How do we organize our files on our like laptop, where it's like all over scattered through a place, but now it's not just an individual problem. You have like a massive organization, could be a healthcare company or medtech company, that just all the files are scattered through the whole different parts of the organization, and you don't have a single view of what kind of data sets do you have. And then now like this, how are you going to generate business value out of it?
And why would it be? It makes sense then that using the tensors would be more robust. And I think that analogy that you just gave of an Excel spreadsheet is really fantastic. But why would it be more efficient?
So now the efficiency comes from this concept. Before, I think 2018, maybe 19, is like when you try to train a model, what you had to do is you had to go and file by file, copy the data from your remote storage to your local machine, maybe spend a couple hours just wasting the compute time that's available for you to have the data transferred to your local machine. And then once it is there, now you can do the training job. But then you get, while also you're doing your training job, your GPUs, which is now the most expensive computation where all these large language models or visual models are running, and they're getting more and more powerful, they get starved. The bigger bottleneck is actually bringing this data to these GPUs to do the training and of the models. And how we do this differently is, once your data is in this tensor format on top of cloud storage, instead of us copying it file by file to your local machine and then you putting this into the GPUs, we can stream the data from remotely. Think of this like Netflix for datasets. Like before that, you have to go and click download, or maybe use a torrent to download the files to your local machine and then watch the movie. Now you can go to Netflix, just click play, and it will start streaming the first bytes or the frames of these images to your browser or to your TV to watch the movie. And the same way now we can feed this to AI models to train the data without them waiting and wasting like thousands of GPU hours of compute until the data will come to the location where they can start training. And then the second thing is, even if you have the data locally, you have to make sure that you ship the data to the GPUs very efficiently. Otherwise, like, I don't know, I heard that recently, like these GPU infrastructures, they start costing like from $1 million to $1 billion. If you follow what Meta is buying like 10,000s of this so-called H100 GPUs from NVIDIA to build their own AI cluster, and having and the biggest problem they have is that when they train those models, the models are underutilizing GPU. So at a time, you might use like 30 or 40% of the capacity that you have. And one of the bottlenecks, not the only one, but one of them is actually bringing the data, like you're not fast enough capturing the data and bringing it to it. So we help to streamline that and unlock the GPUs that are data hungry.
I remember back around 2013, a writer and venture capitalist named Malik, who used to write the GigaOM blog, said that AWS, Amazon Web Services, had taken what he called the table stakes for, a kind of typical tech startup at that time, from around $3 million to around $10,000 to get started. And then, of course, on AWS, you can scale up. Would that be a decent analogy here to what you're saying? You can kind of outsource some of that GPU infrastructure that you would need and complicated technical infrastructure that you need to build in order to run and fine-tune and run these large machine learning and AI models?
Funnily enough, is that because of the AI boom and infrastructure, the clouds are kept catching up with all the trends. So while they did very nicely with traditional web development, the AI infrastructure is still in the early phase, and a lot of companies are figuring out. But what kind of analogy I can deduce for you is the following: like every era of new trend, let's say about 20 years ago it was .com boom, 10 years ago it was the social networks, now we have AI. There's a new computational access pattern that's happening to the data. And since there is no free lunch, meaning that you can't come up with a universal database or any universal system, but in this case, a database that can store all types of different data for all applications, then for every this technological era, there was like a specific database has been created. I mean, you can go back into 50 years ago when then Oracle was created, but then about 20 years ago, there were a lot of web developers. The web developers started working with a lot of this so-called JSON data, which are just dictionaries of different key value items. And there was no any proper storage for that, so people came up with MongoDB, and now MongoDB is a public company. Then about 10 years ago, there's a lot of social analytical information that has been coming to this companies like Facebook or Snapchat and etc. And they were collecting like video gaming companies, all this analytical data, and there was no any appropriate source for this. So data warehouses like Snowflake came to save them, and that created another type of a new database. And our approach was that, hey, AI trend is a new trend. You'll have different types of access patterns, and especially now you will have AI models and now called like AI agents that gonna access this data as well, and they will have a different access pattern that you has been, for example, doing when you're building your own web application. And for that, you need a different type of a database that's specialized for AI applications, and that has been our primary focus for the last 5 years.
Great. So I think at this point in the conversation, some listeners will still be wondering, okay, they're intrigued, but what exactly does Activeloop do? So I don't know if you've seen this, but there is a series on YouTube that Wired Magazine puts out where complicated concepts like quantum physics, for example, are explained to a grade school student, a high school student, someone in undergrad, graduate, then PhD level. If you had to explain in, let's say, kind of the most basic terms, what is it that Activeloop and your Deep Lake product is doing?
Yeah, we actually asked one of our customers, unfortunately I can't name them, but the credit goes to them. So can you explain in your own words what Activeloop and Deep Lake does for you? And they're a big organization. They have a lot of different data types, including from biomedical imaging data to unstructured complex data types, a lot of PDFs, etc. So that's something that you won't be able to fit into an Excel sheet to process with. And we asked them, what do we do for you? And the most surprising answer for them is like, we think of Activeloop as like a magical box or a closet. We throw the data to Deep Lake. It gets organized such that later when we access it, we can very quickly retrieve it, either to visualize or to give it to a model to train it. So in some sense, we are like a closet or IKEA that we give to these organizations better and easier ways to organize their data for AI applications.
And not to pick on an incumbent, but let's draw a difference between what you're doing at Activeloop with Deep Lake and, let's say, at this point, a little bit more of a traditional database like MongoDB. What would be the major difference there?
Mm-hmm. So, for example, if you compare with MongoDB, MongoDB is great for using storing documents and JSON data inside it. It can also support storing vectors where you can do run search. As a primary use case, web developers, they are storing all their web data, their web application like user data. We also use internally MongoDB. It's great for building your own web app. And I'll never recommend, let's say, like some user that wants to build their own website to do, I don't know, let's say build a small, I don't know, social network pretty quickly, use Deep Lake behind the scenes. That will be just waste of like tools in a different environment. But once you go into more AI applications, more specifically, let's say you are building your retrieval augmented generation task. Think of this as just a big enterprise search across all your scientific internal data. And the data can get to terabytes of scale, like billions of rows. Then putting this data inside a MongoDB, it will be like tens, if not hundreds times more expensive than putting into Deep Lake and putting on your own cold storage. Given that architecture of Deep Lake is very, very different. So what we have seen from working with customers is that, first of all, aside from being able to store images, video, audio in a native AI format, we are, because of our compute and storage isolation, we can be up to 5 times cheaper. And you don't always have the need to have a server that's always keeping running while holding your data in the memory. You can store this data in cold storage, which is way more cost efficient, but then you pay the trade-off is with the latency. So if you have an application that doesn't really need this immediate response back to you, it can wait maybe under a second, but not more, then you can use Deep Lake. But if you really need this under 100 millisecond user interface that you need to give, and you need to keep the memory pretty hot in terms of its availability, then go use a traditional database like MongoDB or Postgres. So it really boils down to what's your use case, how you're gonna, where do you gonna store the data, and how you're gonna access it. And if for certain use cases, especially the use cases related to AI and generative AI applications and training your own large language models, etc., then Deep Lake becomes way more cost efficient and good use of a tool versus more traditional databases that there exist.
And being that this is the medical AI podcast, let's talk about the application. So in healthcare, let's talk about that. In healthcare, I mean, think about the different data formats that you could be dealing with. You could be talking about text notes on a patient. You could be talking about transcripts. You could be talking about, a patient's overall electronic health records. You could be talking about MRIs, CAT scans, things of that nature, like you brought up earlier. There are all these different formats. So is this a pretty new advancement, especially when it comes to building machine learning and AI models, that you would be able to put in all of these different data formats and interact with them? And what previously was a lot of that potential just being left by the wayside as a result of limited data formats?
Yeah, so what happened is the following. This was an interesting discovery for us as well. Like we put Deep Lake open source, and then we found that some engineers, especially one of the most exciting ones that we have been working with, Stefan from Bayer, he put a request or an issue saying, "Hey guys, you don't support DICOM files. Can you add that support?" And DICOM files are those container format that when, let's say, an MRI scanner takes the image of a patient, then it gets stored inside a DICOM file, and then it can have a plethora of ways of how to store this data. So traditionally, like in a hospital, you will have a PAC system where we'll collect all the DICOM files, and then it will connect to your electronic health record system, and then give a single patient view of all your history, of all the scans that you have done, plus the data that you have. This works great for like if you want to look into a single patient. When you train a model, is the inverse problem. Here, what you want to do is you want to be able to look into hundreds or thousands or ideally millions of patients at the same time and find patterns or learn those patterns. So then you can train better classifiers or diagnostics tools. The one that I mentioned about cancer detection, and there are like millions of other applications in biomedical healthcare. But what we didn't realize when we were building Deep Lake, even me coming from quote unquote like biomedical background, is that Deep Lake will be still very, very useful for healthcare, medtech, and life science companies. And the main reasoning, what we realized afterwards, was that while you had all these traditional tools like the databases that we talked about, focused on more technically cool and exciting use cases, such as like web development, they did pay very little attention to more like mission critical, highly valuable, like highly impactful industries and areas such as healthcare. And more specifically, also, there's a lot of regulations that you need to take care of, handling the data, and there's a lot of overhead. So all the like smart brains and the like human intelligence went into building this very, very solid data infrastructure tools, such as databases, like take an example like MongoDB or Postgres or Snowflake, that work very well for, let's say, Silicon Valley type of use cases. But the handling and taking care of all this long tail of different modality of data that you very frequently find in healthcare has been like sort of neglected. And it's also understandable because you have so many different formats. You have like each organization and each tool, like a medical tool, like stores the data in a very, very different way. And it's so hard to organize the data that people just like kind of went with the flow. And it has been hard now. You have relatively new, but they are no longer new. Data scientists now need to train models for medical use cases, and they have to deal with this problem. And when we talk to more engineers in this space, what we found out that they're building their own custom pipelines. They are not reusable. Like they might even build a pipeline they themselves can't use like after a month because they don't understand the code, how it processes the data. And I'm not talking about even sharing the pipelines with other team members, because like you can't just single alone. Like I don't know if you've seen these research papers, but you have now tens of people in every single like a foundational model research paper, because it requires you a collaboration of a huge organization to work together to be able to train those models. And what we realize is one of their biggest pain points is going from this old existing systems, including PACS, to take out all the DICOM imaging data, for example, and giving this to the models. And you also, by the way, it's not just you take the files and put it into a model and everything works great. In order for you to be able to build the FDA compliant, production ready models, you have to take care of the biases. Let's say you have to take care of if, for example, there's the imaging that you fed into a model, is it has it been like, for example, 80% male and then I don't know, 19% female? Has it been the case? Then you have to like make sure that you adjust this to be 50-50. So during the production, there's no any bias these models have, or it could be not even patient related, but also it could be related to the scanner itself. Like, is this MRI scanner that I'm using coming from this vendor? Can I make sure that I have an equal distribution of this MRI scanners that fed into the model itself? Because later when I deploy this model, I don't want to, I don't know, think that my model always only has seen like the Siemens MRI scanner, but hasn't seen others in the space. So you have to take care of all this edge cases, and that the whole infrastructure has been missing there. That's what we realized. And then the data engineers and deep learning engineers had to suffer through building all these different pipelines for every single use case. And that has been creating a lot of complexity and a lot of overhead for them. And what we said is, why don't we take care of all this, like the boring but important work for you, so that then they can focus on the most critical and especially important is figuring out how to make these models very accurate and making sure that they are FDA compliant and they can be deployed into the hospitals and help patients actually cure diseases. And that's the biggest goal and ambition that these companies specifically have, and we are also more than super excited to contribute to that goal.
Yeah, I think that's such an interesting point about the biases, and something that in the, public conversation about AI probably isn't talked about enough. And healthcare is such an interesting example of that, where, you think about this really as a powerful engine that could also point you in the wrong direction if mistrained. If and you could end up really using incredibly advanced technology to move backwards if you're not careful. I think the example about using a certain brand of machine, for instance, or not being representative enough in demographic data to come to worthwhile conclusions. So I think that's a really interesting point. Also, while you were talking through that, a thought that crossed my mind was, let's just say we are talking about a hospital network here that they want to build and fine tune a very complex model, maybe for a very specific use case, right? So for a specific disease detection, that sort of thing. Like, how does it kind of work, not just from a technical, but from a like a workflow process, right? Can this stuff be automated, that it's all being fed into building this model and being fed into your database, or does that still take a lot of manual actions on the ground? Everybody make sure that you're adding this data to the right place. Does that make sense, what I'm asking?
Yeah, totally. So it's difficult to comment on a single hospital level. That will be ideal. I think that's where the dream is, and that's where the whole industry is moving forward. That once a new patient data has been captured, then it can fed to, in an anonymous way, preserving privacy, to a model that can be learned or improved. And then at every diagnosis that a doctor provides, these models become so good that at some point they bypass the human level capabilities, and they can do better diagnostics, or more like interventions as well when required to cure the humans. So that's the future. What currently happening is way more complicated in terms of these workflows. Is that the data initially being captured, then there's a like the de-anonymization that's happening from the data itself, removing all the private information under regulations. Then this is passed to a company or a startup, could be, that's has the kind of capabilities to train those models, because you also need a very highly expertise of deep learning scientists to be able to train those models. It has been very rare that we have seen a hospital having those people on board. And likely also the data that comes from a single hospital is not enough. So this data is captured between this, let's say, an organization that collects either from the hospitals or the clinical trials or from the various processes they do have. And then only after the data has been anonymized, it can be stored in our storage, but it's not managed by us. Our deep lake is deployed to this company who has access to the data, so we don't see the data. One of the key benefits that comes from the architecture that we have, that I mentioned previously, is that the data and the computation, everything is happening on the our customers' on premises or on their cloud. So we don't see the data doesn't fly to us either whenever it's visualized or it's queried or it's streamed to the training models. Everything is happening on customer infrastructure, and it makes us like way more secure and way more reliable and also compliant with the regulations that you have in terms of managing this data. And having said that, unfortunately, we are not there yet where as a data coming into a hospital, you can trigger that whole workflow to get everything set up. But I think that's a very good framework to think, how can we enable that? How can we make sure that every decision that in the past the doctors made can be actually ultimately fed into a model or a system that can self-improve, self-learn. And if we are optimizing, hey, we have to make the best decisions for all the patients, if that's the goal. And the reason why I'm saying this is that, yes, it could be felt threatening as well, that some of the like medical personnel or doctors might feel that their jobs are automated. But the way I see that, we are super far from AI models making their own decisions on the patients. I feel there could be better like assistants that can kind of cover the knowledge requirement that necessarily have. And I'll give you a very trivial example as well. Like when you go to a hospital with some rare disease that they have never seen, they might give you their prescription, or just give you a protocol, follow a protocol that does this. But if that was a very experienced doctor that has seen this rare case, he will have, or she will have known the right workflow or the protocol that needs to be followed, or maybe come up with the right strategy how to tackle the disease. And I have been myself, and I know a lot of my friends have been misdiagnosed because of these generic protocols. And I think there was another story as well recently that there are like order of 40 million misdiagnoses from radiology data every year. And if we had an AI model, obviously it won't be perfect from day zero, but it could be to the point that it's better, has a superhuman accuracy, and can be better on figuring out this edge cases and failure scenarios, and then make better decisions there. So I think to get to that point, in terms of the workflow and the system, is that you have to build your own data engine. And data engine here, we'll borrow a concept from self-driving cars. The way Tesla has been built their self-driving capabilities obviously took them more than what they expected initially. But the key step that they did initially is that they built this infrastructure that can collect data from the millions of cars that they have in the production, to collect this data and then train these models and then deploy it back, and then collect more when these models are misbehaving or creating, let's say, failure scenarios, and then collect these edge cases and bring back. And I don't know if you have been following recently the demo they did, is that one of the examples they brought is like whenever you see initially in the first model they trained end-to-end these neural networks, they didn't stop at a stop sign. And the reason for that is that since it was trained on human behavior data, more or less the average driver was not stopping at a stop sign, and that's what it learned from. And then they manually, the way they solve this problem is not, they will write code saying that, hey, whenever you see a stop sign, you actually need to stop 3 seconds there. They started upsampling more examples or scenarios where actually this, like, now we'll call it rare drivers actually stop near the stop sign legally. And then they upsample this data and fed to this model. So the model now, if you use an FSD, it will actually stop the nearest stop sign like for 3 seconds before driving, and that's what according to the driving rules. So the conclusion here is that you need to build your own data engine similar to what Tesla has been built, and then start feeding all these rare and edge cases, and as you said as well, have a full representation of patient information. So then these models, when deployed in production, can actually do better than humans do. And for that, you not only need a single hospital, not maybe in a state hospital, but like you need all hospitals working together to be able to capture this data and improve the systems and to make them as good as humans do. And hopefully, and that's where biggest bet is on AI, is that it can actually, in the very domain-specific use cases, do better than an average human can do. So yeah, I think that's a long answer to your short question, but it is like, I think that in short, the goal is there. We are not there yet. There's a lot of work that has to be done to get there, and one of the key ingredients for us to get there is to be able to create this data engine and this loop where as the new data comes in, which is sampled from these rare cases, can be fed into a model, and the model gets improved, and then you find the other edge cases, and then you do this loop until it becomes as good or better than humans.
Well, without any evidence, I have a suspicion that Tesla was training on driver inputs from here in Denver, because I've never lived in a city where people fly through red lights so often. I like it's when a light turns green, I don't even press the gas immediately. I just wait now for someone just to come flying through the intersection. So, yeah, imitating human actions might not be the best. I'm happy you brought up Tesla, because that's an interesting example, and for a question that I have for you, because both with Tesla and then another example that we could use is, say, with pilots, right? We all appreciate great pilots. A lot of flying could technically be done in an automated fashion at this point. Doesn't matter, because at a psychological level for the masses, and I know this is true for me, I'll speak for myself, but everyone I talk to, for the most part, feels the same way. I still want a pilot on the plane. I want a Captain Solly to land us in the Hudson, right, if we need to. And even if technically we were there, which we probably are, or very close to it, the plane could fly and land and take off itself, I'd still feel more comfortable with the patient there. And that speaks to, I think, where we are psychologically with Tesla, for example. We could get to a point in the very near-term future where the statistics are, without a doubt, we could get to a place where, without a doubt, the statistics are better. The death, the crashes, all of that are better. It's still, I don't think in most people's heads, will be a one-to-one comparison for a long time. I think that if a car on a vehicle on full self-driving flies through a stop sign and causes a huge pileup and 6 people are dead, I still just don't think that is the same psychologically for most people as a human doing that yet. And this is my own view. I don't think it will be for a little bit. And that relates back to the AI in healthcare, where you brought up earlier, which I completely agree with, which is, yes, we're going to be augmenting right now more so than replacing physicians, right? And that's the role that it seems like you think, and that's the role that I think AI will play. Now, these models need to be trained correctly, like you said. We have to watch out for biases, like you said. But they also have to be interpretable to clinicians. It'll be difficult for clinicians to act on the outputs of AI models without understanding how the AI models came to those conclusions. And maybe the AI models will, also get a lot better at explaining that. But some of these recommendations and outputs are going to be based on such a complex string of analyses that it's going to be difficult to say, here's how I got to that conclusion, without saying, do you have 20,000 hours to sit down so I can explain this to you? What do you get where I'm going with that? And how do we make sure that the clinicians understand what is being recommended from these models?
Great, you brought this topic. I think there are two key concepts that you have mentioned, that I'll address them both. There's the first one is the emotional intelligence that comes from the physicians, or the human interactions that you're doing with others. And I'll get back to this in a second. And then the second one is the causal understanding of those models when they do make decisions. And there's a fundamental problem with the deep learning, which uses statistics, and the statistics in general that is based on correlations. But for you to be able to make any correct decision, very likely that a human is using causation or causal thinking to do that, so then you can easily attribute what actually caused you to make this decision. And since statistics is based on correlations, then machine learning, deep learning, and the large language models, GPT-4s, etc., they're all inherently correlation models. So even if you can make them interpretable, and there are various tools and methodology and frameworks to do that, they technically or fundamentally have a flaw. They are not causal thinkers. So now, what does it mean? I think that still statistically, it's highly possible that they will do better than humans. It's also still, like, I don't know if you've already seen this GPT-4 models or MedPalm tool, like they can pass the USMLE tests where physicians, they take, after they get their MD, take this course, the exam to be able to get into their internships at hospitals. So there's definitely the promise, or the direction is right. But I think there is some ceiling that needs a few more technological innovations or iterations to be able to come to a point where those models are actually can distinguish between, like, imagine you see like millions of videos of how the apple falls from a tree. Instead of thinking that it's the tree that pushes the apple down, it's actually there exists a gravity that pulls this the apple to the ground. Or there's a way more famous example inside medicine is like, does smoking actually cause cancer or not? And for this, in the current state of the art, is that those models are not capable of figuring that out. Yes, they will give you some response. They will say, hey, I looked into these attributes, that's why I came up with this, but they are not inherently causal. So, and I think that's why currently the way the physicians should be able to use those tools, treat them as tools, and they should augment the knowledge, but eventually the decision owner and the driver is the physician, and you need to trust their ownership to be able to make various certain decisions. So that's the reasoning part. Now, the emotional intelligence is a separately huge topic itself that I don't think that we consciously think about it, but the reason why, at least my perspective, so correct me here wrong, the reason that you will prefer to have a pilot is because there's another human, you trust humans, and then you can talk to this pilot in case of any emergency, and there's another human being is on the other side and can recognize and solve this, like they will solve as if you were there, but with the experience of a pilot, which is true. But I want to bring that another alternative case is like, I don't know how many times happened to you, but when I call to a bank and the customer support person takes the phone call and tries to resolve a problem that I have, that sometimes it could be the case that it's not in their standard protocols. I feel I'm talking to a robot, and there's no way this robot is flexible or tries to understand me. I mean, the human now like tries to understand me and try to solve my problem. And I don't have the same feeling when I'm interacting with GPT-4. Like the GPT-4 experience that I have, I'm not saying for all cases, but for some cases, it has more compassion and a goal to actually solve the problem that I came to ask this, to solve for it. there's a lot of security and reliability issues and implications, etc., to get this deployed even in a bank. But currently, there has been certainly cases where for me, a customer support call has been drained me down. And I wish there was like, hey, if there was GPT-4 was there, we would have figured it out both best for me and the backend. There will be an optimal solution there. So coming back, now I actually have friends who are working on company that they have a lot of data they collect from the patient interactions, and they understand the value of the emotional intelligence or EQ of physicians when they interact with the patients. And the bet is that these models can actually capture those interactions as well and be more human than some of the, I don't want to say everyone, but basically I believe that there will be a state where you will believe and trust more at some point. I don't know, it will be in the next 10 years or 20 years or 30 years, but definitely within this century, is that you'll trust the AI doctor way more than the human. And the basic reason I'll give you, for example, like I go to a physician and they gave me saying, like, they look at all the same data and they give me saying that, hey, you have a cancer. And then you go to another hospital and they look at exactly the same data and they say you don't have a cancer, you have some other problem. And now you are in a dilemma, like, which physician do I trust? Which therapy should I go to? And I know people who like got into very troublesome situations while they like, fortunately they had no any serious problems, but they got misdiagnosed in very severe ways. So I think looking at those examples, and I also had a grandpa who was like always saying that the best physician or doctor is you yourself. And I didn't get why he was saying that, because I was like, oh no, that these people have a lot of experience. They have seen a lot of cases. They can do better decisions for you. But from their side, they're also like handling, I don't know, hundreds of patients every day. They are trying to optimize for everyone's help. And sometimes they have to take sacrifices. And that becomes a very challenging, that's a very challenging profession to be at. And at some cases, like, if you can achieve like AI agents to be as good as with emotional intelligence as humans, while be much, much better. So in self-driving cars, if you get the same way as the human driver is, that's not good enough, as you said, because one fatal mistake is gonna cause like a big amplified problem for like people not to trust those models. So you need to be 10x or 100x better than an average human driver. So then these fatal errors are so less that you actually are saving way more people than people would expect to save while you deploy this self-driving automotive models into the production. So it's similar to the here as well. If the emotional intelligence is the same level as the human, but the reasoning and causal capabilities are significantly better than an average physician, then myself, I'll much prefer trust the AI model than a human.
Well, you said a lot there that's really valuable. A few things. One, I'm sorry to hear that you've had negative experiences with bank customer service. I usually quite enjoy those conversations, as I think most people do. Two, I would love to have you back on at a certain point to talk about when you were talking about yourself. I'm joking about the bank customer service, by the way. I think everybody gets pretty frustrated on those calls. I think when you were talking about you being the best doctor for yourself, in a sense, love to have you back on another time, and we could maybe talk about how some of these models are built and are going to enable personalized medicine. I think that's a really interesting development in this. But to wrap up the conversation, I want to ask you two kind of rapid fire questions. And I'll go in order. I'll ask the first one, you answer, and then I'll ask the second one. The first is, it says on your website, and I'm assuming you endorse this statement, I agree with this statement, you say competitive businesses, quote, competitive businesses are not built on open AI APIs. Briefly, what do you mean by that?
I think the main reason is that there's a commoditization that's happening. While everyone has access to the same models, then you need to build a big differentiator based on your use case and the problem that you are solving for your own customers. And the big way to solve this is that you have your own proprietary data that you have collected, and you need to train or fine-tune those models to make them much better and give you a business differentiator.
Excellent. And last question, you, Activeloop, you're the CEO. You just raised a Series A of $11 million. That brings your total funding to around $20 million. You have some excellent investors, including Y Combinator. What is on the horizon for Activeloop? What should listeners be looking out for?
We are doing significant changes into our core product Deep Lake. So the version 4 is coming soon, and that's we are super excited. And not only that, it's going to be if hopefully one of the best, if not the best, data lake for deep learning applications, but also we are doing significant effort into making it very useful for biomedical use cases, to the point that that a data scientist doesn't necessarily requiring all the data engineering skills to use the product should be able to use it. So I'm super excited within next 6 months to give this to our customer and user hands, and get their feedback and iterations of hopefully having much bigger impact we had so far.
Well, Davit, I appreciate you joining me on the Medical AI podcast. Congratulations to you and your team at Activeloop, and we hope you'll join us again in the future.
Likewise, really enjoy this conversation and looking forward to connect back again.
Thank you for listening. This has been the Medical AI podcast. We are Felix Beecher and Joe McKeating. Ping us on LinkedIn if you have any ideas on new guests. See you next time.